Hello everyone, and welcome to today's webinar on Total Reflection X-ray Fluorescence, TXRF. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Lori Bisaha, one of our senior scientists at EAG, will be answering some of the questions during the presentation. We will also collect these questions and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Dr. William Warner, Senior Scientist at EAG Laboratories.
All right, thank you, Rena, and thank you everyone for joining us today. I'm going to be talking about total reflection X-ray fluorescence, which I'm going to refer to throughout the presentation just simply as TXRF. So I want to start off a little bit about, who's the man behind the curtain today. And my name is Bill Werner. I'm a senior scientist here at EAG. I have over 10 years of experience in materials characterization. Funny enough, my PhD is actually in geoscience. I received from Stony Brook University back in New York. And here at EAG, I specialize in TXRF, XRD, and XRR. So let's start with an outline of what I'm going to go over in today's webinar. So I'm just going to start with a quick introduction to EAG, then going to take us through the SMART chart, then give just a little bit about TXRF fundamentals so we can understand, exactly what's going on during a measurement. Then I'm going to go through our instrumentation and our sample requirements. I'm going to highlight some real-world examples and show off what we can do with TXRF. I'm also going to cover potential issues we tend to run into with TXRF. It's not a perfect technique, but it's a fairly great technique. Then going to go with some complementary techniques that can collect similar data to TXRF, and then finally end with a summary highlighting the strengths and limitations of TXRF. So let's start first with, who are we? Who is EAG? So we're a Eurofins company. We are a global scientific services company with labs and business development locations across the globe. We have over 20 locations. Most of our labs are centered in the United States, but we do have labs in Europe, in France and the Netherlands, and we have a couple labs in Asia, in Shanghai and Hsinchu, Taiwan. So we serve over 4,000 clients in 50 different countries. But one thing to highlight here with TXRF, it's only available in one location, and that's in Sunnyvale, California, at the heart of Silicon Valley. So let's start talking about the SMART chart, which is our unifying figure across all of our webinars that we've been giving this year. And so SMART stands for spectroscopy, microscopy, analytical resolution tool. And it shows the techniques we have available at EAG, plotted to show their attributes related to both detection limit and analytical spot size. Another way to think about SMART, which I prefer a little bit, is think of it as show me all the right techniques. So to go over the SMART chart here, on the x-axis on the bottom, we have our analytical spot size. This ranges from 1 centimeter all the way down to about 1 angstrom. On the left-hand side, we're looking at detection range in atoms per cubic centimeter. And on the right here is a concentration axis where we're going from 100 atomic percent down to the 10 parts per trillion. So you see the bubbles of our different techniques are color-coded. So Most of them you can see here are blue, and these are techniques that give elemental information. We also have our orange techniques, which give chemical bonding and molecular and structural information as well. So it's hard to group every technique we do just to within this chart. So we have some techniques sitting on the outside of the chart. So in the bottom here, mostly in green are our imaging techniques. So these have a specific analytical spot size they're capable of, but tend to give results in a different dimension. And on the right here, we have our bulk techniques, which tend to not have a fixed analytical spot size, but do have a specific range that they can characterize in the concentration, where we can see something like GDMS goes down to 10 parts per trillion. So what we're going to be talking about today on the smart chart is TXRF, now highlighted in blue on the right side. And TXRF is a non-destructive elemental survey technique that we utilize for quantifying trace level surface contamination on semiconductor wafers and thin films. Now we have it shown here on the right in concentration. We don't report results in concentration. As we're looking at semiconductor wafers, we give results in areal density, which would be atoms per squared centimeter. Now the smart chart covers the X and Y dimensions, but we also always have to consider the Z direction, or the depth of the analysis. So depending on the technique chosen, we can go through various depths of techniques. So here I'm highlighting TXRF on the chart. This is a surface to near surface technique. Typically, we don't penetrate any deeper than 5 nanometers into a sample. But depending on your analytical requirements, a better technique where you want to look deeper and look at the bulk of the sample, SIMS can make sense. Or if you really want to stay very top surface limited or to the top physical monolayer, TOF SIMS might be a better choice. But always keep in mind that the depth of analysis is very important. So let's move on to the applications of TXRF. So as I said, this is for quantifying elemental contamination on the surface of wafers. So we can characterize elements spanning from sodium to uranium. And as I was saying before, we report this in areal density. So this is atoms per centimeter squared. And these wafers can be from various semiconductor process steps. It can be a bare wafer, it can have implant, it could be after chemical and mechanical polishing, etch, thermal treatment, CVD. But as long as it's still considered a type of blanket wafer, we can analyze it with TXRF. And with the substrates and thin films, we're no longer limited to just silicon, as many instruments were in the past. We can analyze glass, sapphire, silicon carbide, gallium arsenide, indium phosphide, just about any substrate there is. And we can also look at many thin films on the substrate, such as hafnium oxide, niobium, gallium nitride. And it doesn't matter if the thin films are amorphous, polycrystalline, or epitaxial. Now, the biggest strength of TXRF is we have the ability to map the distribution of elements on the surface of an entire wafer. So we employ a multi-point analysis that we can select and we can customize and just cover either the entire surface or maybe even just characterize a wedge of a wafer. And finally, I want to point out that TXRF is extremely sensitive to particles on the surface of a wafer. We can pick up a single particle that's, even just 100 microns by 100 microns on the surface, which, can be both a great thing and problematic if you can't always handle your samples in a clean room environment. So next I want to go over the fundamentals of TXRF and just walk through what's actually happening with the sample when we're studying it. So first we're going to highlight the X-ray fluorescence process. And what we have here is we're showing an atom. And what happens is we have our incident X-ray come in, it ejects an inner shell electron, which becomes an emitted photoelectron, which is what gets measured during XPS measurements. This atom is then in an excited state, and then what we have happen is an outer shell electron drops down into the inner shell, and it emits a fluorescent X-ray. So the energy or wavelengths of these fluorescent X-rays is both specific to the element this is occurring in, as well as what the actual shell transition itself is. So to highlight an example, I've drawn out iron here, just showing the K, L, and M levels. This is a bit of an oversimplification of the orbitals, but I just want to point out that when we have an electron transition from, say, the L level to the K level, which is what's being shown in this last image here, we emit an iron K alpha photon, and this has a specific energy of 6.4 keV. Now, if we happen to have a transition from the M level to the K level, that's an iron K beta photon with an energy of 7.06 keV. So that would be coming from like the outer shell here and into the inner shell. And we can of course have more transitions. So shown last here in blue is the transition from the M level to the L level. So this would be an iron L alpha photon, which has an energy of 0.71 keV. And what I want to note with the energies of all these specific photons is as I was saying, it's specific to the elements. And the trend we see is if we move right on the periodic table to cobalt, the energies of the cobalt K alpha and K beta peaks, K beta photons are higher than that of iron. And if you go to the left and look at manganese, you see that the manganese K alpha and K beta energies are lower than that of iron. And this is the trend that we follow across the periodic table. And all of these energies and relative intensities of these photons are all well characterized, and that's how we can quantify the results. So we've talked about XRF. Now, where does the total reflection part come into this process? And so since we only want to look at the surface of a wafer, what happens is we bring in our primary X-ray beam and we reflect it off the surface of the sample. So it's occurring at a very shallow angle, typically something like 0.05 degrees or 0.1 degrees, so that we are below the critical angle, which is the angle at which X-rays will start penetrating into a sample. So we reflect this incident X-ray beam off the sample surface, and we have an energy dispersive detector that sits about 1 millimeter above the surface, and that collimates the fluorescent X-rays to the analytical location. And so this is where the survey part of this analytical technique comes in, is that the energy dispersive detector is sorting all the photons according to energy. So we get a full spectrum of all the photons coming off the sample at once. Now I want to highlight our TXRF instrumentation and the sample requirements. So we've actually been conducting TXRF analysis since the early 90s, going through many different instruments. And we recently upgraded to a Rigaku TXRF 310 instrument, which is shown here on the left. It's a very nice, shiny mirrored box for the most part. This sits in a class 10 clean room so that we don't risk outside contamination of your samples. And just showing here on the front of the instrument, we have 2 different load ports. So we have a load port dedicated to 300 millimeter wafers and one dedicated to 200 millimeter and smaller wafers. So the sample requirements to go over for TXRF and for our instrument is this is a wafer, and you can have thin films on them, only technique. The wafers have to be both flat and smooth. You need to be able to see your reflection in them. But unfortunately, we can't look at patterned wafers because of all the edges that are present. We get a lot of diffuse scattering, and we end up having X-rays penetrating, microns deep into samples because of that. And then we have just the signal overloading the detector. So unfortunately, we can't look at patterned wafers. The other thing to address is the wafers need to be flat. So if these wafers happen to be strained or significantly bowed, say due to a strained epi layer, we can't collect TXRF on these samples as well. So we have a height restriction in the machine. So all of the samples that we run, our max thickness is only 2 millimeters. So no large or strange parts can be run through the instrument. And to highlight the capabilities of this instrument, it's a 1 centimeter diameter analytical spot. The wafer sizes that we can handle are anything in between 50 millimeters up to 300 millimeter wafers. And a new option we're offering that we can now do with our new Rigaku tool is we can analyze any location on a 200 millimeter and a 300 millimeter wafer. So we can analyze directly on the edge now. And I'll show an example of this later in the talk. But unfortunately for wafers smaller than 200 millimeters, we have a 1 centimeter edge exclusion. So that's how close we can center the beam relative to the edge of a sample. And we have 3 excitation energies now from our tungsten rotating anode. Typically in the past we only had 2. Our new addition is what we call our low energy beam 1 path that can handle the light elements now. So relative to the past, we couldn't analyze sodium, magnesium, or aluminum on the surface of wafers, but now with this new beam path, we can. So let's highlight what elements we can look at, as well as kind of what the general detection limits are. So here's a color coordinated periodic table. So and the colors correspond to which beam, which energy is used to analyze and quantify that element. So we have our low energy beam 1 at 1.78 keV. This is what we use to analyze sodium, magnesium, and aluminum. Unfortunately, we can only use it to look at those 3 elements. But you look at, beam 2 at 9.67 keV and beam 3 at 24 keV, and we can fill out most of the periodic table between those 2 beam paths. So beam 2 carries from silicon to zinc, and then rhodium through the lanthanides. And beam 3 we use to characterize gallium through ruthenium, and then tantalum through the first 4 actinides up to uranium. And so I want to note the detection limits, the numbers, below each element here are in 10 to the 10 atoms per centimeter squared. Again, we're looking at areal density, and I want to note that these are detection limits on silicon. Detection limits are calculated for every location where we're analyzing on a sample. So this will vary, so these can vary between locations on a sample if there are any changes in roughness, and as well they can be different between different substrates. Detection limits on gallium arsenide are not the same as those on silicon, but this serves as a good starting point to understand the capabilities of TXRF. So I also want to discuss the 2 modes which we operate in TXRF. So we can call these our measurement types. We have what we kind of call our standard mode. This is where we're trying to get the best detection limits possible. And we look at 3 points on the surface of a wafer. So the example here, this is a 100 millimeter wafer, and the analytical spot sizes in red are to scale. So typically we're recording 1,000 seconds a point, which is the max at which you can collect on the instrument. And then we have our mapping, which here is shown a 49 point map on the 100 millimeter wafer. And I would say we still have good detection limits. There's a step down of a factor of like 2 to 3 between a standard and a mapping measurement. And so with mapping, we can do a variable number of points. We can look at any points on the wafer owing to the restrictions I discussed earlier. And typically we're collecting data for 300 seconds or less per point. So the question begs, what does the data look like? What would I get, for results if we're conducting TXRF on my samples? So I'm going to start stepping through results for the different beam paths I discussed. So this is an example of some light elements on a silicon wafer. So this is beam 1 results, and what we're showing here is the energy dispersive spectra. So here we have its energy in keV versus intensity in counts, and we see it's only going from 0.5 to 2 keV. And what we see here in the pattern is you can see this very strong peak labeled tungsten M, and so this is our incident beam energy that the detector picks up. And then we have a peak for aluminum, magnesium, and sodium being just above the background. And we typically relay this information in the form of charts as well. So we'll list out the location on the wafer if we're looking at multiple points. So in this case, this was at the center of the wafer, X and Y are 0. And then we just list out what the quantified numbers are. So sodium here is 51 e to the 10 atoms per centimeter squared, magnesium 92, and aluminum 507. And then we list at the bottom what the calculated detection limits are as well for the sample. And so this is a straightforward view of beam 1 data. Now I'm stepping over to beam 2 data, which is the most commonly requested because this has the ability to quantify transition metals. And so here I'm showing an example of what we could call a clean silicon wafer. As a client, this is what you're hoping to see. You're not hoping to see major metal contamination on the surface of your wafer. So in this pattern here, we're going from 1 keV to 10 keV. And again, this large peak all the way on the right is our incident beam energy, our tungsten L beta. And on the left, you can see another large peak going off the screen. And this is actually the silicon peak from our substrate. So we can see here in the pattern, we only have peaks from sulfur and chlorine, no transition metals, with a slight rise in the background here. And we report this up in the table here. I've just listed out what are the commonly requested metals and showing only results for sulfur and chlorine. And we list everything else as ND, meaning not detected. So there's another phenomenon that I'll also discuss later in the presentation. As you see here, there's a peak called Si K alpha plus. And this is what's called a sum peak. And this is coming from our silicon substrate. So unfortunately, energy dispersive detectors aren't perfect. And sometimes you have the case where 2 photons reach the surface of the detector at the same time. And instead of being counted as 2 different photons each with their own individual energy, the detector will count them as 1 photon with the combined energy of both photons. So in this case, silicon K alpha sum peak has an energy of 3.48 keV, which is just twice that of the 1.74 keV of the main silicon peak. Now, thankfully, this is something we know and understand and can characterize so that it doesn't interfere with the quantification of elements that happen to be near in energy. So we see the silicon sum peak actually straddles potassium and calcium. And so since we understand it, we can model it and therefore not affect the detection limits and quantification of potassium and calcium. So far I've only shown examples from silicon, but I also want to highlight other substrates we look at. So here are results from a sapphire wafer. Unfortunately, it's a fairly dirty sapphire wafer. So again, we're showing the energy in keV from 1 to 10 keV. But in this case, for the substrate peak, we see, we don't have a strong silicon peak. Since this is sapphire, we have a strong aluminum peak. And so this also shows off that we can quantify silicon on the surface of sapphire wafers. And we see here, unfortunately, this wafer pretty much has every element ranging from silicon to zinc on the surface of it. Most cases well over the detection limits. So this is the typical table we would show. And just to remind you again, units are in e to the 10 atoms per centimeter squared. So outside of sapphire, one of our other most common non-silicon substrates that gets requested is gallium arsenide. And gallium arsenide is a little different than the other two. What we see here with gallium arsenide is we see an elevated background, and we also see a strange background shape. So we see that there's a rise here in the background, instead of with the what you'd notice on the silicon and sapphire examples, that the background just follows this curve coming off the tungsten L beta peak and then flattening out. So this kind of strange background hump is actually due to resonant Raman scattering from the gallium atoms. So it's an odd phenomenon where the incident beam energy is very close to an absorption edge on gallium. And so some gallium actually ends up absorbing the incident photon to create an excited state, which then decays, which then gives off a bit of a continuum of different energies at lower energy. So the good news is the software knows this, understands the math behind it, and we can fit the background so that we can still properly quantify zinc, nickel, and the tag hiding behind this peak here is copper. So one last spectral example, I wanted to show off what beam 3 data looks like. This is our high energy beam, 24 keV. So this is an example of a silicon wafer that I purposely contaminated with zirconium and niobium. So we're showing here the energy range is going from 8 keV to 20 keV. There's not much excitement going on here, but we can see a few peaks are present. We see a very low amount of bromine just above the detection limits, so 1.5 e to the 10. We see a nice strong zirconium peak. This is quantifies at about 192 e to the 10 atoms per centimeter squared. And we also get a weak niobium peak that shows up just a bit over detection limits at 4.3 e to the 10 atoms. So what I've wanted to show you over the past few slides is this is what generally what our spectrum looks like. We provide these to clients as well as the tables at the top here as well. But I want to highlight, one of the strengths of TXRF now, which is the mapping capability. So here I've shown that same 49-point map, the locations on the 100mm silicon wafer. I've just taken a spectra from this blue location here, which is at roughly 20 minus 20 in X and Y. We can see plenty of contamination on here as well. We see sulfur, chlorine, potassium, calcium, titanium, iron, zinc, plenty of surface contamination. So what we do with all this integrated data is we can generate heat maps showing the location and concentration of each of these elements. So here I've shown 9 different heat maps from sulfur to zinc, and blue is at the bottom of the scale near the detection limit, and you get the increase towards red, showing higher concentration. So what we can see from these maps is this can help you locate exactly where your contamination is from, help you determine the source. And then, comparing all these maps, you can then see what kind of correlations exist between the different elements and what that can tell you. So in this case, we can look at, sulfur and calcium seem to have the same 3 main hotspots and seem to be mostly distributed across the surface of the wafer. Whereas if you look at, there appears to be a relation between chlorine and potassium. They have the same 2 main hotspots. And you can look across the other elements. Magnesium and iron seem to have a relation also to chromium. But zinc could probably be characterized as a combination of almost all the hot zones that we see here. So another example I wanted to bring up is including edge measurements and mapping. So here's an example of a 177-point map on a 200mm silicon wafer. So what I'm trying to highlight here is you can see all along the edge is we actually centered the analytical location right on the edge of the wafer. And from that, we collected beam 1 data because I was interested in looking at the distribution of sodium, magnesium, and aluminum. And we see here highlighted in the maps is we do have contamination on some edge locations. So we have a major sodium peak here on the edge. Magnesium is mostly not on the edge except for that same site on sodium. And we see aluminum is a bit more widespread with several edge locations having contamination. So this edge measurement is a new capability for us that we are offering now, and I just wanted to show it off for any of you who are interested in looking at edge contamination. Now with TXRF, the examples I've shown look fairly smooth and straightforward. That's not always the case. We do run into interferences, and sometimes this can, hinder us, and sometimes we, have ways we can compensate for it. So, in still talking about the light elements, I want to talk about light element spectral interference. So, again, showing here a beam 1 spectra from 0.8 to 2 keV. And what I want to highlight is we have major interferences between all 3 light elements. So here is the location of an aluminum peak, and I'm highlighting that bromine L lines interfere with aluminum. So if you happen to have high bromine on the sample, you're going to have a peak in the same exact location as aluminum, which can complicate things. In the case of magnesium, arsenic will interfere with its quantification. And for sodium, if the sample is high in zinc, that will interfere with its quantification. Now, the good news is, in this case, these overlaps can actually be corrected by collecting data with beams 2 and 3, which are the beams you have to use to quantify both arsenic, zinc, and bromine. And so by determining the number there, we know the relative height, the relative intensity correlation between that concentration. So we can actually end up deconvoluting any peaks that are present here. So we can actually separate, the bromine peak from the aluminum peak and still provide quantification. Now, since there is overlap, it does raise the detection limit, but it doesn't make the measurement impossible. So I'm going to show a more extreme example now, talking about overlaps in some peaks. And this is a question we probably get once a month at this point, which is looking to quantify iron, chromium, and cobalt, either in the presence of high tin contamination or on a tin film. So what we see here in this beam 2 data is we actually have a handful of tin peaks that are on the left side of the pattern. It's tin going down the line to about 4.5 keV. So unfortunately, all these tin peaks disrupt any quantification of calcium, potassium, scandium, and just about to titanium. But most clients aren't interested in this case in those elements, but they want to know these higher energy elements, the chromium, iron, and cobalt. So let's zoom in a little bit down towards the background here and look at the peaks. So this is over the same scale. We can see our iron peak here. And looking at the spectra, we see a peak here. This is where the chromium peak is. This is where cobalt is. It would look like that we do actually have chromium and cobalt. The problem is, which the software can't label in this case, is we actually have these tin sum peaks. So they occur, we have one here that doesn't interfere with anyone, but they also occur exactly at chromium and exactly at cobalt energies. So unfortunately, these strong tin peaks interfere with the quantification of chromium and cobalt. Now, the good news is none of these sum peaks interfere with iron. So you can quantify iron on a tin surface or something with high tin contamination. Now, the only time that won't work is if you happen to have an argon implant in the layer. So I've highlighted an argon where the argon peak would be. This is the argon K alpha at about 2.9 keV. And unfortunately, you can run into the possibility where you have a sum peak between argon and the strongest tin peak, which would then be at the exact energy of iron. So that would then interfere with any quantification of trace iron. So I just wanted to show here that, interferences happen. We can overcome some of them. Some of them we can spot that aren't typically characterized. But if you have an interesting sample like this, just ask us beforehand and we can give you, some advice on, if it's going to work, if this is the best technique or not. And then I want to go into some questions we commonly get as well. I'll term it as odd wafer or non-wafer TXRF. So we get requests for wafer backside analysis, which if the backside of the wafer is polished, this isn't a problem. We can load the wafer in, upside down and, say map the surface. However, some smaller wafers have unpolished backsides, rough backsides. We can sometimes run these rough backsides. I'd say we have about a 50% success rate. Unfortunately, since the surfaces are rough, you get deeper penetration of X-rays and a lot more diffuse scatter. So you run the risk of overloading the detector with X-rays. So in cases where it is a rough backside, we just recommend performing a handling test if that's what you're looking for, just on a wafer that's flipped over so that you run the polished side of the wafer, through your instrument and your handling, and then we can analyze that side. We also get inquiries about mapping trace contamination on large parts, say like a big aluminum beam in a semiconductor manufacturing instrument. We can't put an aluminum beam in the instrument, it's meant just for wafers, but we have had success doing contact transfer from these large samples. So what we do in this case is we take silicon wafers that are clean and just press them against the part and then note exactly where on the part it's touching. And so we've actually done this with 300mm wafers on a 1 meter long aluminum beam. And by running these contact silicon wafers, we're actually able to trace the location of the contamination up the sample almost half a meter to its main source. So there are indirect ways we can get around looking at trace contamination in a large part. It's not always the best way to go about it, but we can handle it. And the last question I want to address is, can you collect TXRF data on a photomask? So outright, the answer is no. Photomasks, reticles tend to be too thick. But if you can thin the photomask to be 1 millimeter thick, we can custom etch a pocket in a silicon wafer that can hold the sample and carry it through our instrument. And we have to thin it to 1 millimeter because remember, we have this 2 millimeter height restriction. So this seems a bit outlandish, but it has been tested and it does work. It may not be useful for spot checks on a photomask, but if you're trying to hunt down, systematic contamination on a photomask, perhaps a particle contamination, this can be a way to locate it. So I also want to touch on complementary techniques to TXRF. Here at EAG, I would say we have 2 complementary techniques. That would be TOF SIMS, the big orange bubble here, and dynamic SIMS. There are webinars available on the website that we've already given on both techniques. TOF SIMS has a smaller analytical area. You see the largest here is 1 millimeter versus the 1 centimeter for TXRF. But TOF SIMS doesn't just look at elemental information. You can also get molecular information, and you can get even small, highly detailed ion maps as well. And I've also included dynamic SIMS here, as this is more of a highly sensitive bulk technique on a wafer, but there are modes of dynamic SIMS where you can just focus on the surface of a wafer for certain elements, but it's also a great bulk evaluation of wafers, which could be in tandem with TXRF. So one more related technique I want to talk about that commonly comes up is VPD ICP-MS, so vapor phase decomposition ICP-MS. And what that does is that employs a droplet of acid on the surface of the wafer that it then drags all over the surface of the wafer on its entirety and dissolves the contaminants on the surface, and then ultimately collects this droplet and runs it through an ICP-MS. So this can get detection limits similar to that in TXRF, and actually in some cases can exceed TXRF detection limits. But if you're choosing between these 2 types of techniques, there's a couple things you have to consider. Do you need a destructive versus a non-destructive analysis? When it comes to VPD and dissolving the surface of a sample, you have to consider, will this substrate actually go into solution? Is it something I can easily dissolve? There's well-known parameters for handling silicon, but other substrates can't easily be dissolved or safely be dissolved as well. So is your analysis, do you want this to be location specific, or are you looking for a general average of your entire wafer? And then thinking about some of the stuff I showed with TXRF, are you going to run into possible spectral interferences for what you expect on the sample? So which choice between these 2 techniques is always going to be sample and goal specific. There's no real hardline rule what might be best for you, but I would say reach out to us, we can help you figure it out. And so finally, I want to end on a TXRF summary, and these are the points, if you take anything away from today's webinar, this is what I'd like you to remember. So TXRF, this is a surface elemental survey analysis. It has a wide element coverage from sodium to uranium. It is non-destructive, and it employs a 1 centimeter spot size, which we can also utilize into mapping options on larger wafers. Our instrument resides in a class 10 clean room, so that we don't risk any additional contamination on your samples. Everything is handled in a clean room. We can now take direct edge measurements on 200 and 300 millimeter wafers. And here at the bottom of the strengths, which can also be a limitation, is we are sensitive to surface particles. So we can characterize surface particles if that's the contamination you're concerned with. But the other side of that coin is if you're not handling this sample entirely in a clean room and doing so properly, your wafer can pick up other surface particles that aren't related to the contamination you're looking for. So listening through the possible limitations of TXRF is this is a polished wafers, thin film only technique. I highlighted earlier some ways we can get around it and look at other things, but for the most part, you want to think this is a wafer technique. In some cases, we have spectral interferences that can limit element quantification. And unfortunately, our minimum size is 50 millimeters. But it could be a 50 millimeter coupon. It doesn't necessarily have to be a 50 millimeter round wafer. And finally, while we can detect some lower Z elements now, particularly sodium, magnesium, and aluminum, we can't detect anything lower than sodium at this point. So one of the last questions is, why choose EAG? There's several reasons that we list here in this slide, but it's important to state, from the beginning that client confidentiality is core to our business. We understand IP. We take protecting it, very seriously. We have over 40 years experience in the materials characterization business. And one other thing I want to highlight is we are ISO accredited. So if that's something that's necessary for your research, we do have the proper accreditations we can share with you to prove it. And just before moving on, I want to address the global elephant in the room, which is COVID-19. So I'm going to say we are still operating and have been operating this entire time, all of our labs across the world. We are operating at a bit of reduced personnel capacity, and we are following all federal, state, and local regulations, as well as any CDC recommendations. But one of the things we are limiting are on-site client visits. So right now, you can drop off samples or ship them to us. You can't come on site and say if you wanted to observe an analysis, we unfortunately can't allow you in the building at this time.